lecture series on differential equations. Today's topic is numerical method for Laplace and Poisson equations. We had seen in partial differential equations that we are not getting many analytical methods in which we can get the solution of differential equations in closed form. Rather, in using this Laplace equation, we had find it out that we are getting the solutions in the form of the Fourier series or in the form of infinite series, where the coefficients we are obtaining as the Fourier coefficients of the functions which are being defined as the boundary conditions or the initial conditions, and from this infinite series we are trying to give the solutions. So, finding out the closed form solution is not easy in many times. What it says is we are approximating the solutions. Approximating the solution says is that if we are given at certain points, can we really find out the solution at those points, or that says is move to the numerical methods. So, first what is the numerical method? Numerical methods are methods for solving the problems numerically, giving solutions as the numbers or graphs. That is, rather than getting the functions, we would get the solution as at particular points. This is the solution at this point, this is the solution, or we are saying is that graph, that is at those points whatever the solutions we are getting, we do join them with the showing the graphs. So, this is what we are calling the numerical methods. Now, today we will discuss two equations, Laplace equation, which the two dimensional one first we will take, because in the last lectures we had seen that Laplace equation we are getting the solutions in the form of infinite series, whether it may be two dimensional or three dimensional. So, let us first discuss with the two dimensional del 2 u over del x 2 plus del 2 u over del y 2 is equal to 0, or the Poisson equation, that is non-homogeneous Laplace equation del 2 u over del x 2 plus del 2 u over del y 2 is equal to f x y. Numerical method says is solving the problem numerically. What we mean by solving the problem numerically, if you see is that is here what we are saying is the function, unknown function for which we have to solve this equation, that has to be a continuous function. Not only the continuous, it must possess the second order derivative, so that it satisfies this equation. But when we are solving it numerically, what we are saying is that we are knowing the function or knowing the conditions, and we would actually give the solution at certain points only. So, what it says is that these things we have to actually discretize, that is this continuous problem we have to discretize, so that we can suitably get certain equations which we can solve numerically. So, that says is change these continuous problems, that is these models which we have got from the physical problems, change these models to the discrete problems. So, this change of the models with the discrete problems in the discrete, to make it a discrete problem, either we could say is we start our modeling with the discrete method itself, or first we modeled as here as the continuous mathematical model from the physical conditions and then discretize it. So, we are using it here is that is first it has been modeled as the mathematical model as the differential equation, and then we are going to discretize. Discretize here means is that is we are talking about the partial differential equations. So, in this case discretization says is that we would like to write this derivatives in the forms of difference coefficient. The partial derivatives we have to change to the difference quotients. What are the difference quotients and what is this? Let us see. We do know that is using the Taylor series expansion for the two function of two variable, that we can write u x plus h comma y as u x y plus h times u x x comma y, that is the partial derivative of u with respect to x at the point x y plus h square upon factorial to u x x x comma y and plus h cube upon factorial 3 the third derivative, partial derivative with respect to x of u at x y and so on. This is the Taylor series expansion of the function u x y, where the we have taken the extension as x plus h at the point x y. Similarly, if I take u x minus h y, we do get the expansion is u x comma y minus h times u x x comma y plus h square upon factorial 2 u x x comma y minus h cube upon factorial 3 third partial derivative of u with respect to x at x comma y and so on. Now, we have to find out the difference coefficient, as I said, that is we would actually try to find out the partial derivatives with respect to x of this unknown function u in the form of the function at the point x plus h comma y and x minus h comma y, that is at certain points, that is what we are saying. So, let us see, if I subtract from the first equation, that is if I write u x plus h comma y minus u x minus h comma y, what we would get? U x y, this term will get it, cancel it out. This term we will get 2 times h times u x x comma y, then this again the third term would cancel it out, then we would get plus 2 h cube upon factorial 3 times the third partial derivative with respect to x into y and so on. Now, so from here what we say is, that is if I take in this subtraction the h term I do take and higher powers of h I neglect, then I can approximate this u x y as 1 upon 2 h u x plus h comma y minus u x minus h comma y. What we have done is we have subtracted these two, and what we are getting is the series 2 h times u x comma y plus 2 h cube upon factorial 3 times the third derivative partial derivative with respect to x of at x comma y and so on. So, if I take h is such a small that higher powers of h, that is h cube and so on, they are very small as comparison to this one, that they would make this term to be 0 or negligible, we could approximate it like this one. So, we have taken this 2 h right hand side. Now, if you do see how we are defining our derivatives, if we just go to the analysis, we define the derivative of f with respect to x as f of x plus h minus f x divided by h limit as h approaches to 0. That is what we are doing over here. So, what we are approximating it only with the first one, rather than saying it as h approaches to 0, we just write it as approximately with this one. Similarly, if I add these two, I would be getting 2 times x into y, this term would get it, cancel it out, then we would be getting is 2 times h square upon factorial 2, the second derivative of partial derivative of u with respect to x at x comma y, because 2 times h square upon factorial t, I would get it only h square and so on we would be getting. Now, again if I neglect the higher powers of h, that is h square we do retain, but h to the power 4 and so on we say is that they are very small or negligible, I would get the addition of u x plus h plus u x minus h y would be 2 x y and then plus h square times u x x x comma y. So, from here we will approximate the second derivative. So, u x x x comma y we could say approximate as 1 upon h square u x plus h comma y plus u x minus h comma y minus 2 u x comma y. So, this says is, that is again if you see is, that is what we could write it as u x plus h comma y minus u x y minus u x minus minus u x y minus u x minus h comma y. So, we are just having as the second derivative with respect to x of u, this we are approximating, these we would call difference quotients. Similarly, for y, again now what we will use? We will use the Taylor series for y. So, rather than having u x plus h, we would have u of x comma y plus k. Now, we would be writing the Taylor series with respect to y. So, the derivatives of y, u x comma y plus k times u y at x comma y plus k square by factorial 2, second derivative with respect to y at x comma y plus k cube by 3 by factorial 3 times the third partial derivative with respect to y at x comma y and so on. Similarly, if I take u x y minus k, I would get u x y minus k times u y at x y plus k square upon factorial times u y y at x y minus k cube upon factorial 3 times the third partial derivative with respect to y at x y and so on. Now, again use the similar method, that is first I subtract from u x y plus k to u x y minus k, that would give me the approximation for the first partial derivative with respect to y, and that would be 1 upon 2 k u x comma y plus k minus u x comma y minus k. And if I add them and neglect the higher powers of k, that is k to the power 4 and so on, we would get the approximation for the second partial derivative of u with respect to y. U y y as at x comma y is being approximated as 1 upon k square u x comma y plus k plus u x comma y minus k minus 2 u x comma y. Now, we have got our u x x and u y y. Now, first we will see the numerical method for the Laplace equation. The points which we are using in this difference equation, we are having the point u x, that point x y, the point x plus h, the point x minus h, the point y plus k and the point y minus k in all this difference quotients. If I was using only the first difference quotient, that is u x, we are using only 2 points, either these 2 points or these 2 points. When we are using the second derivative, we are using all the 1, 2, 3 these points and these points. So, if I use all the points in our Laplace equation, we would be getting it all the 5 points. So, let us see, these are the points which we are using in different quotients, difference quotients. So, Laplace equation is del 2 u over del x 2 plus del 2 u over del y 2. So, that is, it is u x x and this is u y y. Now, change it to the difference quotients. U x x is 1 upon h square u x plus h comma y plus u x minus h comma y minus 2 u x comma y. U y y is 1 upon k square u x comma y plus k plus u x comma y minus k minus 2 u x comma y. Now, what we would be doing is, at the first stage we have taken is, that is for the x axis we have taken the difference as h and for y we have taken the difference as k. Now, if I assume that is take the difference, both the difference same, that is h and k as same constant, then this equation we could change as 1 upon h square to u x plus h comma y plus u x comma y plus h plus u x minus h comma y plus u x comma y minus k minus 4 u times x comma y, this is equal to 0. Now, you see, I have not gone, that is first writing this one and then writing this one. So, we could say that is we could write this plus this plus this plus this and then minus 4 u x y. We had used in this manner. Why you see is, that is we have used in this manner, you will find out that this is easy to move around. First we are increasing this on the x axis, then we are moving to the y axis, then we are moving to the x axis, and then that is we are following this anti-clockwise motion in this, writing this difference quotient and writing this Laplace equation. Now, since it is equal to 0, this 1 upon h square term will go out because h is not 0. So, if I multiply it over here, what we would be getting is u x plus h comma y plus u x comma y plus h plus u x minus h comma y plus u x comma y minus h minus 4 times u x y is equal to 0. So, we are getting is this 5 points, 5-point formula for Laplace equation. What this 5-point approximation? Again we just move, as I said is that it is easy to find out, that is right in that manner. We are starting from here. We could say is, if we just go in our usual notion of the maps, we are saying is this side is east, north, west and south. So, we say is east, north, west, south in the same direction, we could find out the formula. This 5-point approximation we are using for our Laplace equation. If it is a Poisson equation, then the right hand side is not 0, rather it would be some h square f x y. So, for both of these things we would be using this our 5-point approximation. This 5-point approximation from here, if you to see, we are saying is this is 1, this is 1, this is 1, this is 1 and this is minus 4 times point at function at x y. So, the pattern, or this is being also called the stencil, we could just get it from here. You see is 1 1 1 1 and minus 4. This is called the stencil, or you could say pattern, or the mesh points. So, we are changing now our equation, this u x plus h comma y plus u x comma y plus h plus u x minus h comma y plus u x comma y minus h minus 4 u x comma y is equal to 0. We could write it as 1, this matrix you say, that is wherever the points have been left, they are 0, 0 1 0 1 minus 4 1 0 1 0 times u is equal to 0. This is at a point x y. So, now if I had been given different points x y, that is if I give this problem for many values of x and y, these kind of patterns for each x y we would get. Now, if I join all those x y, we would get some you could say algebraic equations which would give me, that is at the different points. So, here it is at u x y. So, similarly at one x y, then another x y, then another x y, we do get the equations, and since this is giving us the relationship between the point x y and its right hand point, left hand point, upper point, lower point. So, we do say is that if I take the this point and the next point is this one, then this point is also related with this point is related with this point, and so on, we do get a relationship. So, let us see is how we are going to discretize this Laplace problem over here. So, as I said is that east, north, west, south, that is what we are getting is a simplified form. Similarly, the Poisson equation, as I said, is do have only non-homogeneous, that is the right hand side is a function of x at x and y. So, now whatever the point x and y we are talking about, we take the evaluate the value of the function at those points, and then what we do get is this Poisson equation would simply move as u x plus h comma y plus u x comma y plus h plus u x minus h comma y plus u x comma y minus h minus 4 u x y is equal to h square f x y. So, if I write in those notation of the stencil, I do get it as 0 1 0 1 minus 4 1 1 u is equal to h square f x y. So, from here now see, that is what we have done. Let us move, that is how we are going to really solve all Laplace equation. So, we do know that practically if we are solving this Laplace equation or Poisson equation, either we are solving a Drichlet problem, that is using certain boundary conditions. So, first we would be doing it with the 2 dimensional one. So, if we are moving to this boundary conditions, so whatever be this boundary is been given, that is whatever reason on which this Laplace equation has been defined, so that the Drichlet problem has been defined, we first choose h and define a grid. See, suppose this is the plane on which the boundary condition is being given, Drichlet problem. Drichlet problem says is that my boundary condition is defined on this boundary, that is the curve. So, what we do is we choose first h. So, here for simplicity I am using a small region. So, let us say this h I have chosen very large one, so that I could cover it up. From 0 0 we are starting, let us say this 5 h we have used. So, this point we would to call P 1 1. So, what it is? It is actually the point you see x plus h, y plus h. This point is x plus h, y plus 2 h, this point is x plus 2 h, y plus h, and so on. So, we write it as 1 1 1 2 and so on, and now what we do take is, since h is that common we have taken, so we are not writing it as 1, what we do call this point as p 0 0, this point as p 1 1. So, what we are saying is in this grid, first we have defined this grid, divided the whole region into the smaller regions that we are calling grid, like this one small square is of the size h cross h. Then these cross points of this grid, these points are being called mesh points or the nodes. And now what we do is we take this equation, define this equation at all these mesh points. That would actually result me, as I said, is if I am using this at this point and this point, then this point would use this point, while as the relationship the differential equation with the difference quotient would be using at this point would be using this point. So, actually we would be getting is algebraic equation. So, if I use this difference equation at nodes to get the relation, so this is how we are using it now. So, at the point Pij, suppose if I am using Pij is, that is I h from the on the x, that is u x plus I h y plus j k. So, there the point would be u I j. So, here if I use, then east point, that means from here the right point means I plus 1 and j is as such. Then this point I is as such, but j is moved to j plus 1, that is I times j plus 1. Then this point I is as such, j is as such, but I is I minus 1. So, u I minus 1 j, and then the lower point where it is u I j minus 1 minus 4 u I j is equal to 0. So, we have got this relationship. Now, for all I and j inside this boundary, that is wherever this problem is being defined, we can find it out. This will result me actually in algebraic equations. We could check it, that is with a little bit insight we could see is, that is all those points whatever we are getting is we would get the number of equations equal to the number of unknowns which we have to find out. That is what we would actually find out in the numerical solution, the value of the unknown function u at these points. So, we use these relationships as well as the boundary conditions to get the algebraic equation, but the coefficient matrix, as you said, is we find it out that it would be actually 0 1 0 1 minus 4 1 and 0 1 0 like that at u I j. So, if I am taking is u I plus 1 and j plus 1 like that, if I write out all the points wherever which are we interested, we will get more zeros than the non-zeros, that kind of matrix. So, the coefficient matrix we would get more zeros than the non-zero entries. This kind of matrix with, whenever we are cutting, we call it the matrix as sparse. In this kind of sparse matrix, actually the method of elimination, Gauss elimination method, that is very costly in the senses that it will take too much time as well as too much work to get the solution, and we may get somewhere the division by 0 or something like that. So, we may not be able to get the nice solutions. So, this kind of sparse matrices, when we do have a coefficient matrices, then using, rather than using this usual elimination method, we do go with the iteration method. Moreover, here in this one I have taken a small grid. A small grid means is h is large. Now, if you do remember how we have got our this difference quotient, there we have taken is, that is the first derivative as f of x plus h minus f of x minus h upon h. There h has to be small. So, for getting more nice insight about the function u, we require h to be small. If h is small, my grid would be more finer, and that says is I have to have this system of equations very large. Maybe sometimes in very small problems we may be reaching to 100 cross 100 or something is 500 cross 500. So, this sparse matrices, the usual method does not go. Normally, we would like to use the iteration method. How we are going to solve this problem? Let us see it with the help of one example, so that you do get, that is how we are finding out the solution and what the iteration method. Iteration method normally in this Laplace equations are being used are the Gauss-Seidel methods, which in the earlier times used to also be called Liebmann method. So, let us do one example. The four sides of a square plate with side 12 centimeter made of homogeneous material are kept at constant temperature 0 degree and 100 degree as shown in the figure. using a grid of 4 centimeter and applying Liebmann methods, find the steady state temperature at mesh point. So, what is this boundary condition? Boundary condition is been given by this. So, we do have a uniform plate of a uniform material with square plates whose size are 12 centimeter cross 12 centimeter. Its temperature is being kept at 0 degree centigrade and 100 degree centigrade. That is, this upper side is 0 and these 3 boundaries are kept at the 100 degree centigrade. Now, what we want? We want the steady state temperature at mesh points. It says is that numerically we have to solve it. We have already done when we are having is steady state temperature, that means which is independent of time t, then our heat equation, this is actually the temperature or the heat flow, that heat equation is changing to the Laplace equation, 2-dimensional Laplace equation, and the solution of that we have to find out using these boundary conditions, where the boundary is being given here like this one. We had already solved this kind of problem. If you do remember, we have done one example where we had kept other side 0 and the upper side only as some. Here it is the reverse kind of thing. Now, it says is that use a grid of 4 centimeter, that means now I have to divide it into 3 points only. So, let us try one by one. Steady state heat flow equation is Laplace equation. We do know that del u over del t would be 0. So, del 2 u over del x 2 plus del 2 u over del y 2 is equal to 0. This is we have to solve with our boundary condition given by this method, that is what we are saying is u x 0 is 100, u 0 y is 100, u 12 y is 100 and u x 12 is 0. So, this is the boundary condition which is given to us. Now, we have to use the numerical method. So, as said is that this reason we have to define a grid. Grid they are saying is use this h is equal to 4 centimeter. So, if I am using h is equal to 4 centimeter, I would get the grid of 3 cross 3. So, given problem this grid and mesh points we would be getting it 4 centimeter, 4 centimeter, 4 centimeter. So, we would get these 3 cross 3 grid. Now, the points, the first point would say is P10, P20, P11, this would be P01, P02, P12, P22, P21 and P20. And the boundary conditions are being given that at these points, all these points, that is P00, P10 and P20 and P30 we are getting is 100, u at 100. Similarly, at P30, P31 and P32 we would be getting it as 100. Here P00, P01, P02 we are getting is 100, while as here P03, P13, P32 and P33 we would be getting it all 0. So, we have to find out the value of this u at all the mesh points. So, these are the mesh points which we are getting, while as the boundary mesh points we do know that is they have to satisfy this boundary condition. So, finally, what we have to actually get it, we have to get the solution at all the interior inside the points, these 4 points. So, we will use the relationship so that at all these 4 points and for all those 4 points whatever the relationship we are getting in the difference quotients, they would include all these one, and at this one we would use these given boundary conditions. So, let us see how we are going to solve this problem using our method. So, this is what the first step we have done. We have defined the grid and the mesh points. Now, we have to use the difference quotient at all those nodes. So, we will take only the interior points, because at these boundary points we do know that they should satisfy this boundary conditions. So, the solution we are knowing. So, let us find out this relations at all the node points. use this relation ui plus 1 j ui j plus 1 plus ui minus 1 j plus ui j minus 1 minus 4 ui j is equal to 0. So, the first point we will take ui j, that is p 11. So, at p 11 if I do write ui plus 1 I would get p 21, ui this one we will get p 12 and from here p 01. So, get this algebraic equation u21 plus u12 plus u01 plus u10 minus 4 u11 is equal to 0. The second one at p21 we do get it as u31 plus u22 plus u11 plus u20 minus 4 u21 is equal to 0. Then at u12 this p12 point u22 plus u13 plus u02 plus u11 minus 4 u12 and then at p22 we would get u23 plus u32 plus u12 plus u21 minus 4 u22 is equal to 0. Now, we are using the boundary points u01, u10, u02, then u23 and u13 and so on. So, at those boundary points, because we are knowing is that the different boundaries, that is what are the my values at those points. So, let us rewrite these equations. So, here what we will get u21, that means p21 this point, u12 is this point, these 2 points are unknown and u11 these 3 points are unknown, but u01 and u10, u01 means is that is this point, this u10 and u01 both are 100. So, what we do get the solution as this equation as u21 plus u12 minus 4 u11 is equal to minus 200, that is these two I have taken to right hand side. Similarly, here u31 means is we are getting it this point which is 100 and another boundary condition is u20 is this one, again we are getting is boundary condition, that is it is 100. So, what we do get is u22 plus u11 minus 4 u21 is equal to minus 200. Similarly, for the third one u22 plus u11 minus 4 u12 is equal to minus 100 and last one is u21 plus u12 minus 4 u22 is equal to minus 100. Now, we have got these 4 equations and in the 4 unknowns. What are the 4 unknowns? u11, u12, u21 and u22. So, we have got the 4 unknowns, 4 equations in 4 unknowns. So, we can now we solve this equation. So, now let us move, that is how to solve. Let us first see is whether we can get a solution or not. So, let us first use, because it is a simpler and a smaller system, we can go ahead with the Gauss elimination method. So, with the Gauss elimination method we are having these 4 equations, write it in the matrix form, the coefficient matrix. We would get now we are using a pattern, first variable u11, then u21, then u12 and then u22. So, what we get, the coefficient of u11 minus 4, coefficient of u21 is 1, coefficient of u12 is 1, coefficient of u22 here is 0, right hand side is minus 200. Similarly, for the second one we are getting is the coefficient of u22 is 1, coefficient of u11 is 1, coefficient of u21 is minus 4 and coefficient of u12 is 0, so on. So, we do get this system minus 4 1 1 0 1 minus 4 0 1 1 0 minus 4 1 0 1 1 minus 4 and the unknown variable, that is u11 u21 u12 u22 is equal to the right hand side minus 200 minus 200 minus 100 minus 100. Using that elimination method we write this augmented matrix as this one and use the row echelon forms, or that is the row operations. So, using the third one, let us make this first the entry in the first column of the second row and the first row as 0. We do get it as this row is as such, the last row is as such. Here what we have done is we have subtracted from the second row the third row. So, directly subtraction gives me, that is simply it would be 4, this would be 1 minus 1 0, that is, and what we are getting is minus 600 over here, that with this one would be, that is multiplied 4 times and add it up to here, what we would be getting this one. So, here what we do get this as the solution. Now, again use this this entry to make this equation to make this fourth row to make these two entries 0. What we do get 0 0 minus 16 8 0 0 8 minus 16 1 0 minus 4 1 0 1 1 minus 4 minus 500 minus 500 minus 100 minus 100. Now, again we just make use of this equation to make here the entries 0 and 1. So, what we do get it finally we will get first this 0 and then whatever here is been got that divided by that one we get it 1 entry. We do get it 0 0 1 125 by 2 0 0 1 minus 2 125 by 2 1 0 minus 4 1 minus 100 0 1 1 minus 4 is equal to minus 400. So, from here if you do remember our first unknown was u11, u11 we are getting 125 by 2, then the last this sorry u22 and then what we are getting is u12 and u22. So, again we would be getting it. So, what we do get the solution u11 and u21 as 87.5 and u12 and u22 as 62.5. So, from here we were getting 62.5 and from putting all those things back reverse method we would do get. So, this method is simple one, you do know that is how to find out the elimination. So, I had gone a little bit shorter. Our problem example set is to not to use this one, as I said is that this method is not applicable when we are actually doing the problem. So, we want this Liebmann's methods. What is the Liebmann methods? That is simply Gauss-Seidel method, that is iteration method. Iteration method says is what is this Gauss-Seidel method? Gauss-Seidel method says is that these equations which we were solving it, we have to write it in different manner. In the different manner, that is we write u11 in the terms of u21 and u12, then u21 in the terms of u11 and u22 and so on. So, we write the unknown variables u11, u21, u12 and u22 in the form of these other unknown, they are actually in the similar frame. So, we rewrite this equation as this one, let us say from here u11 as 1 by 4 times u21 plus 1 by 4 times u12 and this plus 50. Similarly, this one u21 is 0.25 u11 plus 0.25 u22 plus 50, u12 is 0.25 u11 plus 0.25 u22 plus 25. So, u22 is 0.25 u21 plus 0.25 u12 plus 25. Now, we start with some initial guess. Let us say this initial guess, for example, here we are taking is that all the variables at 100. It may not be very nice guess, but let us say start for the example all the ones, because we are having is that boundary conditions at the 3 points as 100. So, we are starting with the initial guess as 100. Now, what we do is that we get the second iteration, that is the first iteration, we get the first approximation u11, u21, u12 and u22 using these initial guess over here. So, let us say that is how we are getting. We are starting with this initial guess with all these 4 equations. Let us write first u21, u21 at the initial guess is 100. So, first approximation we would be getting it as u11 as 0.25 into 100 plus 0.25 into 100 plus 50, that is 100. Now, when we come to u21, now u21 I will not going to use this u11 at the initial guess, because u11 already we have find out in this iteration as 100. Of course, it is a different matter that we have got it as 100 itself, but we would use this guess u11 at this point. So, u21 we would be getting 0.25 into this 100 plus 0.25, u22 is 100 plus 50, again it is 100. So, the first iteration again we have got u21 also as 100. Then when we are coming at u12, we would use u11 as this 100 and u22 as this 100, because u22 till now we had not find it out, and plus 25 we get it 75. Then we come to u22. u22 we want to use u21, u21 will use this 100 and u12 will use this 75. So, we do get 0.25 into 100 plus 0.25 into 75 plus 25 as 68.75. Now, we have got this first iteration, the first approximation as 100, 100, 75 and 68.75. So, now this we would use in our these equations again. So, now we will use these approximations to find out the second approximation. So, second approximation you do get 0.25 into 100 plus 0.25 into 75 plus 50 as this 93.75. Then U21 I would use this 93.75 rather than this 100, because whatever the second approximation we had already got, and in the second equation, the second iteration itself we can use it this one, so that the convergence, or you could say the solution reaches fast, the calculations becomes fast. So, 0.25 into 93.75 plus 0.25 into 68.75, this is 90.62. Similarly, here we would use this 93.75 and 68.75. So, we are getting it 65.62, and finally, we would use it 90.62 and 65.62 over here, and we do get 60.06. So, like this we would move on and we try to reach to the solution. How to stop it? We are not knowing actual values. What we do is that when in the two iterations, whatever this approximations we are getting very close enough, we say is we do is stop. So, this is what is our this Liebmann methods, which says is that how to find out this solutions in this one. We do know already that my actual solution is 62.5 and 68.5 and 82.5. So, you can, this problem is a little bit simpler one, you already have known, that is how to solve it. So, we can check it using actual Fourier series, that is find it out Fourier method, find out what is the solution, and we can check with there, that is how much near we are reaching to this one. We can improve upon this convergence, or that is reaching to the final solution if we take a better guess. Normally, here we are taking is, that is the guess is starting from the boundary conditions, we are normally taking this better guess. So, you can take this guess. So, like this what we are having is the solution of our Laplace equation. Now, if I have to solve this Poisson equation, what we do get, we will write the difference quotient, and what we do get at that point x y point, whatever the point we have taken, we do get right hand side as h square into f x y, that is the value of the function at that point multiplied with that, what is that h we have taken, h square. So, we do get again the algebraic system, and then we can solve with any iteration method, and we do get the solution. So, this is what is the numerical solution of Laplace equation using one method, iterative method, that we call the Gauss-Seidel method. Here we had used this method because our matrix which we had got, that coefficient matrix in the algebraic equations, were very sparse one. So, one method we had learned today for solving the Laplace equation using the Gauss-Seidel method as to find out the solution of Laplace equation, Drichlet problem actually, where the boundary conditions are being given on a rectangular region. So, we will learn some more methods in the next class. Thank you.